Look at that. The second try was successful. Unlike Chicago Bears field goal attempt at the end of the game yesterday. It was slightly tipped. You're right. It was barely tipped, but he missed the second one. The first one was a timeout. So anyway, how about Nick Foles though? How about Nick? Yeah, they booed him off the field at Soldier Field. Yeah, like the Spurs booed Kawhi every time he touched the ball. Yeah, that was good too. Okay, so we are kind of on the cusp of a new adventure together. What we did the first semester was good and fun, right? We all had good fun, a lot of fun memories. We kind of just did Algebra 2 all over again. So in that case, I guess we could have called it Algebra 3, huh? Maybe if that, or Algebra 2.01. I don't know. What comes after 2? What comes after 2? Lots of things come after 2, right? 3 is 2.1, 3, 1 million comes after 2. So anyway, you can call it whatever you want. But now we're getting into something that is kind of new. It's essentially new in the sense that you haven't really studied it in other classes. Now, geometry, maybe a smidgen, okay? Because we're going to study angles and angle measures, right? Now, you got to read that carefully. We're studying angles, not angels, right? So if you thought we were studying angels, I guess you're in the wrong place. I guess that would be church. I don't know, right? Although we did have a comparative religion class here one time. Miss Kendrick taught it. That was kind of cool. Yeah. So we're not studying angels, although feel free to use them if you still need them. We're going to be studying angles and angle measures. All right. So if you think back long ago, and I'm not talking like last semester, right? Like when we were on the brink of a 2-week vacation. But I'm talking like really long ago, like before calculators, right there, BC. Right? There was no social media, right? So there was no Netflix, there was no football. So what did people your age do when they were? Yeah, they threw rocks at each other. Today is National Old Rock Day, and I don't know if that means like old rocks, like planet Earth is an old rock. Or like old rock and roll. But anyway, yeah, they would throw rocks at each other and like, hey, you got my toga dirty, whatever. But then they got bored, and then when nighttime came, guess what they did? They slept. Very good. All right, I think that's enough for today, just to kind of shake the rust off. No. We had the privilege over the break of having some very, very, very clear, cool nights. Did anyone go outside and take advantage of that? And well, it was comfortable. It was comfortable. It was a perfect night to go pee off the back porch, if nothing else. No? Did anyone look up on the clear nights? Yeah. What did you see? Stars, right. We have stars. Okay. So the stars were kind of like, man, that was a huge show. That was like the internet long ago before the internet, because you looked up and there were so many things there. And, of course, if you stare at them long enough and you eat the right root, you can start seeing patterns, right? Yeah, and that's how the constellations came about. But those things moved, right? They moved. Even when you didn't eat roots, they moved. They were not always in the same place. So people started looking to the heavens, and believe it or not, they weren't just mesmerized by it. They wanted to study it. They wanted to analyze it, and they wanted to figure out how these things moved. And they knew that they came around in cycles, right? And they knew that just like we do, every so often it kind of got cold, and then it got warm, and then it got cold, and then it got warm. So they knew that things were cyclical. They knew that there were seasons, okay? So we could talk about those things as rotating, right? You have seasons that rotate. You have stars that move, that rotate in their orbits, right? So anything that rotates, we have to study it with some new type of math. We have to be able to predict it with a new kind of math. So what are some of the things besides stars and planets and their orbits that you know that rotate? There's no wrong answers here, unless it doesn't rotate. Wheels. Yeah, wheels. Wheels go round and round, right? The wheels on the bus, they go round and round. Good. So if you want to talk about where something is or how fast something's moving that goes round and round, right, you need to be able to talk about nonlinear motion. We call that angular motion, okay? So the study of angles and their measures became kind of important to the early astronomers as they tried to predict the planets. And, of course, later on, when the wheel was invented, they want to know how fast it rotated. That's different from how fast something is moving down the road. So here are some names that you don't have to know. Anyone want to try that? Hipparchus of Nicaea. Yeah. So later on, Constantine went there and had a big religious meeting at Nicaea to establish the unified creed, and they became known as the Nicene Creed. But this was way before that, Hipparchus. So what did he do? He is considered the father of this subject. Okay, let me double highlight that. Trigonometry. There you go. So the second semester is essentially the study of trigonometry. We had Algebra 3 or 2.1 or Algebra 1 million, whatever you want to call it, in the first semester. In the second semester, we call it trigonometry. Okay, now trigonometry is made up of a couple of roots. What's it? Oh, did I update it? I don't even know if I did. No, it just looks different. It's the bulb going out. It makes it look different. All right, so what are some roots in trigonometry that you recognize from other words? Metry, right? Metry, like geometry, right? What do you think metry means? Measure. Very good. Metry means measure, from the Latin word whatever, metry. I don't know, I'm not Latin. Any Latins in here? Okay. And then the first part, trigono. Oh, there's a word in there, no, right? No means no. Just let's get that out there. Guys, no means no. Okay? And then trigono. What does that mean? Trigono. Angles. Yeah, very good. Trigono means angles. Okay? So trigonometry, when you translate it into whatever language, right? Greek, Latin, French, Spanish, it means the study of angle measures. Okay? And this guy, Hipparchus of Nicaea, is known as the father of trigonometry. He was an ancient astronomer, and what he did is he established a set of trigonometric tables. That is, he painfully, empirically recorded the movement of certain celestial bodies, and he wrote them down, like where they were in the sky at this time, where they were in the sky at this time. Okay, so very, very primitive, but he was the first guy to get the ball rolling. And then the word trigonometry actually didn't come along till much later. So at the time, Hipparchus was just known as Hipparchus of Nicaea. It's kind of interesting if you go way back, right? You don't know their last names. It's just like Kevin of New Braunfels, right? Are people going to be reading about that years from now? Probably not, right? Yeah, but then here was help me out, anyone? Bartholomew, right? Or Bart. We can call him Bart, right? And that's maybe what his friends called him. Bart Meniscus. Bart Meniscus of wherever he was from. He published a work in the late 16th century. Right? Y'all know the 16th century is not the 1600s. That's important. If you learn nothing else today, know that the 16th century is not the 1600s. Yeah, I know. Some people don't even ever learn that in life, right? So there you go. This was people are confused. People are like, why? If we're in the 21st century, why is it not 2119? Yeah, I know. Right, I know. So there you go. There's your knowledge kernel of the day. 1595, he published a work called Trigonometria. Yeah, so Latin was the kind of the language of the day. It was the intellectual language of the day. So again, you don't have to know this guy, but Bart introduced the word trigonometria with his published work in 1595. Okay, so here is an actual photo of Hipparchus. Okay, the cameras back in the day were not very, very good, but there is the only known photo of Hipparchus. Okay. No? Oh. Oh, okay. Yeah, maybe I won't update. Okay. All right, by the way, this is the look that I'm going for maybe by the end of the year, just so you know. It's naturally curly. Yeah, it'll naturally curl. So I got a haircut, but I try to stay away from the beard. I hope I don't get that much forehead exposed, but your hairline's gonna scoot down. No, I don't know. I hope not. Yeah, at this point, this guy Hipparchus probably should have shaved his entire head and then just gone with the mustache. But then he wouldn't have been known as the father of trigonometry. He would have been known for like having the first metal band, right? He could have been like the lead guitarist for Slayer, right? If he would have shaved his head and kept the mustache. All right, good thing we're recording all this. Happy New Year, everybody. Welcome back. All right, so my question to all of you is, my question, Lucky Charms. I get excited, and I'm going through puberty, so just leave me alone. So my question is, what is an angle? And don't read down below because that'll spoil the fun. What is an angle, and how do we measure it? So first of all, what is an angle? If trigonometry is the study of angles and their measures, what is an angle? Change in direction. A change in direction. At a certain point. Could be given with an angle, right? That would be something called polar coordinates instead of rectangular coordinates. If you change directions, you can qualify it with an angle. Okay. But what does that angle mean then? What would Okay, so let's go to the second one. How do we measure angles? In what units? Degrees, right? We measure temperature in degrees, but we also measure angles in degrees. So like if you said it's 90 degrees outside, no one would say, oh, so there's a right angle out there, right? Because context clues, right? Context clues. You'd be like, oh, that's kind of hot. But if we said that this angle measures 90 degrees, you would be like, ooh, that's hot, right? No, you wouldn't. You would be like, oh, that's the right angle, right? That's kind of how walls are supposed to be built in construction, but not these, right? Because lowest bidder, right? Probably 87, 88 maybe. Anyway, the painter will fix it, okay? Caulk. I built homes for 2 years before I started teaching. So yeah, the painter's the last guy in the house, so he has to fix everything, right? If the wall's not built plumb or 90 degrees, there's a big gap, you just fill it with caulk, right? The painter will fix it. That was our motto. The painter will fix it. The painter will fix it. Okay, so we measure angles in degrees, and we kind of have an intuitive idea from geometry of what like a 20-degree angle is versus like a 180-degree angle. In fact, when Jason Kidd was first drafted by the Dallas Mavericks long ago, the Dallas Mavericks were a horrible team. This is before Dirk Nowitzki started playing. They were like bottom of the barrel. Jason Kidd was a highly recruited draft, and they asked him, hey, what are you going to do now that you're on the Dallas Mavericks? What influence are you going to have? And he says, well, you know what? We're going to turn this team around 360 degrees. It's a great quote, right? Jason Kidd is one of those guys who thought that the 16th century meant the 1600s, right? We're going to turn this team around 360 degrees. That's not saying much, right? That's saying we're going to keep going in the same direction, because you talked about direction. He meant to say what? 180, right? He meant to say 180 degrees. So in skateboarding, that was a cool trick for a novice, right? A 180. Woo. Okay, right? That's halfway around. So we know how we measure angles, but what is an angle? If you had to define an angle to someone is like, okay, what is an angle? You would say an angle is a what? Maybe it's time to read the box. An angle is a measure of rotation between two rays of a There you go. An angle measures rotation. That's the first thing we need to know. An angle measures rotation. We talked about things that rotate, right? Things that come around cyclically, like tires rotate, seasons rotate, planets rotate. An angle measures that rotation. An angle measures rotation. Now, how do we measure it? Well, we measure it between two rays that share a vertex. So we will kind of tap into a little bit of your Precal knowledge. So let's think about it. What is a ray, first of all? We'll write this up here. Geometry. Yeah, sorry. A point and an arrow. Yeah, it has a fixed end. We call that a fixed end. It's a dot. And then it has an interminable end, okay, which y'all designated with an arrow. So it's like a half of a line, right? It has a fixed end and an interminable end that goes on in some direction, right? So maybe in geometry, you put another dot somewhere on the interminable end, and you labeled the fixed end something like A and B. You would then call this ray AB, and you put an arrow above it. Now, does it matter which way the arrow points in the notation? Yes, right? You draw it like that. That's how you would notate the ray. The fixed end would be A, and then the interminable end would be B, okay? So there's a ray. So now if we draw two rays that share a vertex, let's do this. Draw one coming up here, and then draw one coming down here. And you don't have to label this anymore. We're not going to do that. Notice we have two rays, and they share a vertex now. So the fixed ends we call the vertex right there. And those two could go on forever. So we're not measuring length. We're not measuring length. We want to measure the rotation between there, okay? So that would be essentially one of two things. Most people probably see this first, right? Now notice it doesn't matter if I draw that little arc there or there or there, okay? The rotation is going to be the same. Now, what variable did y'all use to measure or to designate an angle in geometry? You probably abandoned the alphabet as we know it and went Greek, huh? You don't? Okay. Have y'all seen that variable before? Yeah, theta. That's the Greek letter theta. It's like a zero that's going to a formal dinner party. He's wearing a cummerbund only, right? Yeah. He's naked, but he's wearing a cummerbund. So come on in, zero. Thank you. Yeah. Okay, so that's theta. So we typically use a theta, and I'll just draw it right there. Let me get rid of these other ones so you're not confused. Oop, too much. Let me get rid of these. We typically don't draw it like way out there. We typically draw it kind of close to the vertex. But you can label that as theta, okay? And we do measure that in degrees. So from geometry, that would be approximately what? What value can we approximately give to theta here? Yeah, just an approximate. Could I call that 170 degrees? No. If we assume it's drawn to scale, it would have to be what? 80, 70, 87 maybe? Yeah. It looks like it's less than 90, right? 90 is kind of what we use, again, for our frame of reference. It's a right angle, right? Okay, 90 degrees. That one looks like it's less than 90, so we then categorize them by their size. You would call that a what type of angle? Not a blue angle, but an acute angle, right? A very acute angle. Yeah, so a lot of y'all use that in y'all's Christmas stories, right? Acute. So that is an acute angle. It's less than 90 degrees and greater than 0. Okay, an acute angle is between 0 degrees and 90 degrees. Good. Now there's another angle that we have in this situation. Does anyone care to venture where the other angle is? Yeah, this one here. We can also call that. Now, in addition to theta, we also use these variables. That's the fish that you see on the back of cars sometimes. That is the Greek letter alpha. And then one of my favorite letters that we use is the happy B. It's like Tigger. It's B on a pogo stick. That's beta. So we typically use the Greek letters, at least when we're not doing coordinate geometry. We use the Greek letters when we're doing planar geometry. Planar geometry just means like I have it drawn here. Coordinate geometry is when we're doing it on the X and Y axis, which is what trigonometry is all about. So we will get back to X as our variable. But right now, we'll stick with theta, alpha, and beta. And that one there, would we know what theta is? Let's say I knew what, let's say I knew what theta is. Could I then determine what alpha is? What would alpha be? Good, 360 and then degrees. You want to make sure that if you're talking about degrees, you put the little degree bubble there. It's a unit. It's like having feet at the end of something that are legs, right? 360 degrees. It's a unit, and then you would subtract theta from it. Okay, and that would give you what alpha is. So two angles that add up to 90 degrees we call what? Do y'all remember? Hey, man, you're acute. Hey, man, thanks for the compliment. Complementary angles. Hey, you look acute too, right? You're cute. Hey, you're acute too. Hey, thanks for the compliment. They add up to 90 degrees. Two angles that add up to 180, supplementary, right? You got to supplement, you got to add a little bit more supplementary angles. These two angles add up to what? 360. Is there a name for that? There might be. I don't know what it is. It's not that important. But maybe if we read this book here and we knew Latin, maybe he defined it. Two angles that add up to 360. It could be, I don't know, whatever. Okay, good. So you know all that. So now my next question is, if you know, and y'all came in with that knowledge, right? You didn't lose that over Christmas break. If you know that a full rotation, let's write that down, one full rotation is 360 degrees. Y'all knew that. My question then is, why 360? If you were the guy inventing it, maybe you would have said a full rotation is 100 degrees, right? What base system do we use in our counting? 10, base 10, right? It's the Dewey Decimal System. 10. We use base 10, right? How many fingers fingers do it? Sorry, we'll start with fingers. We have 10 fingers, most of us. Some have fewer, some have more. For the most part, on average, we have 10 fingers and 10 toes. So that could be why we started using the decimal system. The entire metric system, right? Metric means measure. The entire metric system is based on base what? Base 10. We talked about scientific notation when we studied exponentials. That was powers of 10, right? The common log is base 10. So base 10 is what we prefer. It's easy to count by tens, right? 10, 20, 30, 40. It's easy to count by powers of 10. 10, 100, 1,000, 10,000, 100,000, so on and so forth. 360 is not as easy, right? Powers of 360, multiples of 360. We could do it, but maybe after 360, unless you're fans of Tony Hawk, you might have to kind of do the math in your head, right? 360, 720. Yeah, and then it's like, wow. Tony Hawk one time did a 1080 in competition. What is that? How many rotations is that? It gets a little hard. But man, if we were the ones inventing it, we could have said one rotation, 100 degrees. Two rotations, 200 degrees. Three rotations, 300 degrees. It would have been a lot easier, right? Why were we not there? I guess we can't decide when we're born, right? I guess it's 360. Once all the way around, it's 360 degrees. Just pulled it out of nowhere, right? Pulled it out of nowhere. Like, here's nowhere. Let me grab inside. 360.
To answer your question, why 360? No reason.
That would be a good first answer. Why 360? No reason. Just random. 360 was laying around, right? It was a Christmas gift that no one wanted. There it is. Okay? Or maybe we can think about it. Remember, this is before internet. This is before pretty much everything, right? You couldn't go to the H-E-B and shop, right? How'd you get your food? You killed stuff, right? Right, you killed stuff, or you grew stuff and then killed it, right? Yeah, because when you eat a plant, I guess you're killing it, right? Yeah. So you're always killing stuff, right? That's the cycle of life. But let's say you wanted to kill a bear for food. Okay? Could you kill the bear year-round? You maybe could if you snuck into his den, right? While he was hibernating. And why would even a bear hibernate? Bears hibernate every year, right? It gets cold. If you were growing crops, could you grow crops in every part of the world year-round? No, you couldn't because of weather. Right, weather. So the seasons were very, very, very important to the ancients. In fact, they thought that it was, originally several gods. And if you still believe that, that's fine. I'm not saying you can't believe in several gods. The god of fertility, right? The god of corn on the cob, whatever. Right? You had to pray to these gods for a good harvest so that you could eat and not die. So seasons were very, very important. So let's go back to Y360. Maybe, right. They tried to keep track of how often it got cold, how often the star was in this position, and it seemed to be cyclical. And when they kept record of how often it occurred, it was around 360, right? Is that what you were going to say? Or do you need to go to the bathroom? Well, that's an after. I don't know if they said, let's make a right angle 90 degrees and then 4 of them is 360. Because you could have divided 100 by 4 and gotten 25, right? A right angle could have been 25. So the 90 degrees is a consequence of why they chose 360. But 360 all the way around kind of makes sense when you think about seasons and a full cycle. A full trip around the sun took approximately 360 days, right? And now we know it to be 365.25. There's something, right? There's something. We have leap years every 4 years, but not every 4 years is a leap year. Did y'all know that? We make corrections, right? So like if it's like 2000 was not a leap year because it was divisible by 100 or something like that. So we make corrections every 4 years, but then we make corrections to the corrections because it's 365.25 blah, blah, blah. Okay? But to them, it was approximately 360. So why didn't they use 361? Divisibility. What were you going to say? It's easier to work with. Divisibility. If you took 361 and you divided it by 4, you're like, ooh. Right? So 360 was approximately one rotation, how long it took the Earth to go around the sun. But it's also amazingly divisible by many, many, many numbers, right? 360 has lots and lots and lots of factors. You could divide it by 2. It's even, right? You could divide it by 6. You could divide it by 10. You could divide it by 4 and still come up with integer values, okay? So that is probably, again, we're just conjecturing, that is probably why 360 was chosen, okay? Now, 360 is also divisible by 60, which is a pretty important number, okay? What is 360 divided by 60? 6, right? Now, 60 is also a number that could have influenced the 360 because 360 is a multiple of 60. The Ancient Babylonians, anyone ever heard of them? Or anyone ever knew one of them? Yeah, right. The Ancient Babylonians were not only ancient and Babylonian, but they were pretty influential in the development of math, okay? And we used base 10, or we use base 10 still, but the Ancient Babylonians, in their mathematical calculations, did not use base 10. Guess which base they used? Not 360. They used base 60. Yeah, the Ancient Babylonians, in their works, which we can still decipher from the cuneiform records that were left behind, they used base 60. Base 60 is not called the decimal system. Does anyone know what base 60 is? It's called the, Sexagesimal or something like that. I don't know if I'm spelling it right. It's called the Sexagesimal System. Here's the important part. Sex. Okay? Right? Yeah, if you've seen National Lampoon's European Vacation in German, sex, S-E-C-H-S, is the number for 6. And they're trying to find the address, which is like 6 Dusseldorf Road or whatever. And so they knock on the door, and they're like, hi, my wife and I are looking for sex. And the lady slams the door in their face. Right? Okay. So 60 is the Sexagesimal System, and that's what the Ancient Babylonians used. Now, 60 is also, as it turns out, a very sexy number. It's a very sexy number. Okay? Because here's why. I know your mind is not going there. Like, what, does it wear lingerie? What? No. 60 is a very sexy number because it also, like 360, has many, many factors. 60 is divisible by 1, of course. Is it divisible by 2? Yeah. Is it divisible by 3? Yes. Is it divisible by 4? Yes. Is it divisible by 5? Yes. Is it divisible by 6? Yes. So 60 apparently is divisible by every single number. Right, we went all the way up to 6. Yeah, then it falls apart at 7, but then you get up to like 10 and it starts working again. So it has many, many factors, and so that's an advantage to using base 60. Yeah. Yes, you may. Just take. I'm still going to use the Jingle Bell candy cane because I didn't want to get rid of that. Okay, so that's still my hall pass. All right. So the Ancient Babylonians used 60, and you may think that 60 is also kind of an arbitrary number, although now 360 makes sense. But because it was a sexy number, that's why they used it. Now, we still have a carryover from the Ancient Babylonians and their Sexagesimal System using base 60. Why, where, and how? Anyone? The sexy number system is still prevalent today in certain circumstances. Anyone? Louder? Time. Right? Some of y'all, not in here, but in other classes, some of y'all watch the clock. You're like, when is this class going to end? Right? Yeah, but in this class, you're like, man, where did the time go? We're having so much fun. We're talking about sex and religion and Bart. Yeah. Clock, time. How many seconds are in a minute? 60. How many minutes are in an hour? 60. How many hours are in 60 hours? 60. See? Yeah, well, that's different. Yeah, that's planet Earth's fault, right? So we still use the Sexagesimal System. The time is kind of a carryover, and of course that could also be another reason why they chose 360 because 360 is a multiple of 60. All right, so here's your definition of a degree. We've talked about a degree. It's time to define it. A degree is a unit of measure of rotation. We're going to have another unit coming along. But a degree is defined to be a unit of angular measure. It measures the rotation between two rays that is equal to 1/360th of a full rotation. That's it. A degree is defined to be 1/360th of a full rotation. And again, that might seem arbitrary, but we've talked about it. So that means that how many degrees are in one full rotation? 360. Right. Okay. So you can kind of take, like, here's Hipparchus with this circle. You could take this circle, and you can, and regardless of the size of the circle, you could draw these rays that terminate on the circumference of the circle, or on the edge of the circle, and you could say that if you do 360 of those, I'm not sure if this one has 360, but it gets very, very hard to draw them, right? But if you did, and you were able to draw 360, you could say that this angle measure here was 1 degree, okay? It takes 360 of those to make it all the way around. And that supposedly was because the length of a full year was approximately 360. Very good. So now we know that we know some information that we didn't know before, right? The 1700s were actually the 18th century. Good. All right, so we're going to measure angles in degrees to start with. Now, we're going to talk about parts of degrees as well. Because if I took one of these, let's say they were 1 degree, and I bisected it or just drew it, another one going down the middle, there's 2 of them, so here's another one goes down the middle, this would be now what? It'd be 1/2 of a degree, right? Or 0.5 degrees. So like I said, the length of the trip around the sun is actually not 365, it's 365.25 something something. So we can also have fractions of degrees. So we're going to be looking at degrees in what's called decimal degrees. So we're going to go back to base 10. And so just like we would say 0.5 degrees, we're going to measure the fraction of a full degree in decimals. Okay? Now, there is another way to measure fractions of degrees besides decimals. And it's not going to be fractions like that. Okay? If you have ever looked at GPS coordinates, right? Anyone ever look at GPS coordinates? Yeah, they might look like this: 36 something, 14 something, 22 something. That's what a GPS coordinate looks like. Anyone know what that means? It's a location. It could be a latitude location or a longitude location, because you can measure both that way. But does anyone know how to read that? 36 full degrees. Good. And that's not the outdoor temperature. What does this mark mean? In construction, it means feet. It means minutes. Good. And this one in construction means inches, but in navigation it means seconds, right? So you would read that as 36 degrees, 14 minutes, and 22 seconds. That's a coordinate. Now notice that's degrees, minutes, seconds. Instead of hours, minutes, seconds, which is how we measure time, we have degrees, minutes, seconds. This is known kind of informally as DMS notation. So this is just another way to measure a fraction of a full degree. The 14 minutes and 22 seconds, that's a way to measure a fraction of a full degree. Just like 14 minutes, 22 seconds is a way to measure a fraction of a full hour. Okay? So we can either measure parts of degrees in decimals, like 0.5, or we can measure those parts in minutes and seconds. Now, if we want to measure it in minutes and seconds, we're going to need to have some conversions here, right? So let's see if we could do that. 1 degree is equal to how many minutes, do you think? Not 360, 60, right? In other words, the degrees here, it's kind of like hours. Okay, and because there's 60 minutes in 1 hour, there's also 60 minutes in 1 degree. And now notice the units I'm using. The degree bubble, for lack of a better term, I'm going to call that the degrubble instead of degree bubble, degrubble. And then we got the hash mark, which is the minutes. All right, so 1 minute is how many seconds, do you reckon? Also 60, okay? And that's just like time. 60 seconds in 1 minute. And we have about 1 minute left today. All right? So what we're going to do tomorrow is we're going to look at how to convert from decimal degrees to degrees, minutes, seconds, and how to go from degrees, minutes, seconds back to decimal degrees. Okay, so before we leave real quickly, an angle is a measure of what? Rotation. Things that come around at regular intervals. Good.